The ongoing imperative to increase productivity within the mining sector is driving a relentless march towards the automation of earth-moving machines. Electric mining shovels are the workhorses of open-cut mining, and they've become the focus of automation under the Australian Coal Association Research Program's Shovel Load Assist project, also known as SLAP.
This project was brought forward, and at the time there was a lot of work going in terms of automation of truck units, but there wasn't any projects happening around the automation of the loading unit, so this sort of fit the piece of the puzzle that we were looking for.
This work is being undertaken by researchers at the University of Queensland in association with Joy Global Surface Mining and through the Cooperative Research Centre for Mining. The vision for the semi-automated mining shovel is to improve upon the decisions and actions performed by a human operator. The reasons for doing this are: first, an automation system can improve upon the decisions needed to control the machine to achieve better compliance to the production plan, reducing costs. Second, an automation system can perform the actions needed to operate the machine with greater precision and speed than a human operator, making the loading process faster, more repeatable, and safer. The automated mining shovel will survey its surrounding terrain to constantly update the mine plan, identify the position and orientation of trucks that arrive to be loaded, autonomously excavate to the mine plan, using the fewest number of passes when loading trucks and placing the load so it is equally distributed, plan and execute positioning moves to optimally extract material, and track other equipment operating around the shovel, such as bulldozers. The steps towards this vision have been realised by several elemental technologies. P&H payload measures the mass of material excavated by the shovel. P&H track shield stops the shovel colliding with itself. Truck shield prevents collisions with trucks being loaded. Dozer shield prevents the shovel colliding with cleanup equipment, such as bulldozers. Auto swing manoeuvres the bucket over the truck tray, releases the load, and returns to the face with the operator having overall supervisory control. And autofill automatically loads trucks without the need for any operator intervention.
There are some elements that we're content to sit at semi-automation level. There are other elements that we are pushing towards the full autonomous scenario. In terms of the shovel, ultimately we would like a fully autonomous shovel, so the current path that we're at with the SLAP project has got us, part of the way down the pathway that we're looking for.
The system uses a digital terrain map that it builds of its surrounds using LiDAR sensors. This terrain map is then analysed for locations where material can be excavated. When a truck arrives, the automation system tracks its position and orientation within the map. A sequence of loading cycles is planned that will fill the truck to its capacity in the shortest possible time. Each loading cycle comprises a motion that places the bucket at an identified digging position, a material excavation sequence that describes the motion of the bucket through the dig face, the identification of a dump point to place the load within the truck, the generation of a trajectory for transiting the bucket from the dig face to the dump point, and the release of the load into the tray. Planning loading cycles is complicated by several factors. When the excavator makes a dig, the material it removes will not exactly match what was planned. After the bucket has left the face, some material will usually collapse, changing the digging face. And when material is dumped to the truck tray, it may not be released exactly where planned and may not flow exactly as predicted. The automation system deals with these changes by continually monitoring the state of its surrounds and replanning its future loading cycles to compensate so that the truck is filled to capacity in a minimum possible time. With the ability to automatically load trucks, the next challenge is in determining how the mining shovel should choose where to move. The research team has started to make progress on this combinatorial decision problem. Here, an industrial robot is mimicking a mining shovel at a small scale in a laboratory, planning how it will autonomously excavate a block of material. Eventually, the algorithms used to construct this mission plan will be deployed on full-scale excavators in production mines. When this is achieved, mining shovels will have effectively been automated. The significant benefits include better safety, reduced operational variability, improved compliance to the mine plan, and faster, more efficient truck loading.
It comes back to those two key issues. One is the safety of our employees. So by automating or semi-automating, we're reducing the number of people that are exposed to high risk. And the second element is the impact on our business performance, which is ultimately reducing our unit cost of production so that our customers get their products cheaper than what they can today.
The journey towards autonomous mining machines continues at pace. The development of autonomous mining shovels has the potential to transform the mining industry and is seen by many as the next big step in mining equipment automation. This work conducted by the Smart Machines Group at the University of Queensland has been made possible by the vision and financial support of the Australian Coal Association Research Program, Joy Global Service Mining and CRCMining.